Okay, Assalamualaikum warahmatullahi wabarakatuh. We're going to continue with a boost converter. So for the boost converter, the arrangement of the components are as displayed in the lecture note here. We have an input voltage connected to the boost inductor. We call it now it's known as a boost inductor. So the voltage, input voltage will be connected to the supply to the boost inductor, and then we have a switch, controllable switch, diode, capacitor, and also the resistor. Right, to continue, we assume that we're going to analyze the circuit with a continuous current mode operation, which is referred to this L now. So previously we have a buck converter. The L is connected to the output side, isn't it? But now the inductor connect to the input side, right? So, and very much I in equals to IL. The input voltage, input current also equals to the inductor current. So we're going to consider the continuous current mode operation, steady state analysis, and capacitor is very large, such that the output voltage ripple is ripple free, which is there is no ripple at the output. So we're going to see a straight output voltage, isn't it? A constant output voltage, and it is higher than the input voltage. So this is a boost converter, so V out is higher than V in, right? So let's consider the circuit when there is a waveform here. So we have when the switch is on, so this is during the switch is on, so this is the pass to your switch, right? So that will be the T on from there to there. So let's look at the circuit, what happens during that time. So when the switch is on, this will appear as a short circuit, isn't it? Okay, it will appear as a short circuit, and therefore there will be a current flow in that loop, and this diode will be reversed by the output voltage, isn't it? Because this is connected to the output voltage, so that voltage will reverse bias the diode, so there will be an open circuit there, and therefore you're going to have a, during turn on, you're going to have two separate circuits. The input side we have plus minus inductor, then it's going to be V in, and going to have VL plus minus, and at the output side you're going to have capacitor and so resistor. So this will be your I naught, and this will be your IC capacitor, isn't it? And therefore we can see that IC equals to what? Negative I naught, isn't it? IC equals to minus I naught, and we know that I naught is V out divided by R, isn't it? So during turn on, we're going to see that two separate circuit, input side and output. From the input side, you have V in plus VL, and therefore, if you take the KVL, you're going to see that minus V in plus VL equals to 0. Therefore, you're going to see that there is a input voltage V in impressed across inductor, and there will be a voltage, input voltage impressed across inductor, causing the current to linearly increase. Look at the waveform now. Okay, so this is your current IL. So because of that, VL equals to V in. So there will be a positive voltage impressed across the inductor, causing the current to linearly rise from IL min to IL max. Okay. All right. So therefore, if you look at the equation, we have VL equals to LdIL over dt equals to V in, and then you integrate, cross multiply, and then you integrate, you get the lower limit will be IL min to IL max, and then for the right hand side you have 0 to T on, and therefore you have this ripple of current IL max minus IL min equals to delta IL V in T on. And now let's consider when the switch is off. So when the switch is off, this will appear as a open circuit, isn't it? So the switch will appear as an open circuit, and therefore there will be a flow of current, and that IL also will force the diode to turn on, and therefore you have a single circuit here. We have V in, your inductor, and then you have this capacitor as well as your resistor parallel, and therefore you have VL there. This is your V in, and here you have plus V out, right? So if you take a KVL, then you have minus V in plus VL plus V out equals to 0. Therefore, VL equals to minus V in plus V out. Is it? Sorry. We have VL equals to plus V in minus V out. And we know that V out greater than V in. So therefore, this is actually a negative voltage. So there is a negative voltage of V in minus V out impressed across your inductor, causing the current to reduce from IL max to IL min during turn off of the switch, right? So if you look at the waveform gain, there you are. So you have your current reduced from IL max to IL min, and this is your T off from there to there, and we have T on there. This is your T. Is it? Okay, so do the KVL gain. So when the switch is off, then we have VL equals to V in minus V out, L dIL over dt, and then now the lower limit is IL max to IL min, V in minus V out, L integrate T on to T, then you solve that, and you equate with equation 10 just now, then you have finally V out equals to V in 1 minus T. So what does it mean? That, so if D equals to 0, then V out equals to V in. Is it? But when D equals to close to 1, if I put it as a 1, then it will be V out equals to infinity, isn't it? Because 1 minus 1 will be 0, so a very, very large output. So you cannot use D equals to 1, and therefore, so you have to avoid D equals to 1 for boost converter, or else you're going to have a very large output voltage and very large output voltage across your switch as well. Okay, so it will be from 0 to not close, not equal to 1, yeah, but it's in between, yeah, to get your output voltage. Okay, right. So before we proceed, let me reiterate on the inductor current. So if you refer back to the circuit, your inductor is actually connected to the supply voltage, isn't it? DC. Sorry. This is your switch, diode, this is your capacitor, and that is your resistor. Right? So now your IL is actually at the input side, and we know that small letter I in also equals to IL. Right? So if I take the average of the current, I in, the capital letter I in, also equals to the average of IL. Right? Because we're going to relate, we want to relate I naught with IL, isn't it? Okay, so we need to establish a few equations so that we can relate between I naught and IL, right? So therefore, there will be a auxiliary equation, additional equation. So we need to set for boost converter, we're going to have assume lossless circuit P in equals to P out. So this is average value. V in, I in equals to V out, I not, I out. So I in, all here is actually the average value. Average value. Right? So therefore, I naught divided by I in equals to, so if you, you use that equation, okay, so if you modify that equation and substitute this equation into that one, then you will have this output, input current and output current, and they are related in with the equation. I naught over I in equals to 1 minus D. Okay, right, so with that in mind, then we're going to look into boundary between continuous and discontinuous current. I think I don't want to repeat the same explanation, right? So again, we always want to for EPO 510, we're going to discuss only continuous current operations, and similar happens here. At the boundary, you're going to have, okay, so if I may sketch the inductor current again, okay, so we have this as a IL max, and this is IL min, isn't it? And the average of IL is always IL equals to IL max plus IL min divided by 2, right? So the average of that waveform. And at critical, again at critical, so we're going to see that your current touches the 0 current, and then it will rise again, isn't it? So this is at the boundary condition, isn't it? Whereby IL min equals to 0, right? So IL min equals 0, and then we have IL critical with respect to that equation. IL critical equals to IL max divided by 2, and from equation 10, if you refer back to your equation 10 and substitute that into the equation 10, then you have IL critical equals to V in P on over 2L, right? And next is that from equation 12, the output voltage equation, you're going to get IL critical equals to V in T on over 2L. So you just replace that V in with V out equals to V in 1 minus D, isn't it? Now, so then you get this equation. But we know that, again, we know that IL also equals to I in. The average of the input current also equals to the average of IL, and therefore you have this statement: IL critical equals to IL. Therefore, replace IL critical, and using that the equation before, by using this equation, okay, so we know that IL critical equals to I in critical. So now you have what? I not critical, there's no I. Okay, so you have I not critical equals to I in equals to 1 minus D, isn't it? And therefore, this is IL. This is IL critical. Okay, so using this equation, right, and then you replace 2 and you substitute into the above this equation. Okay, you replace with this equation, and finally you found out that I not critical equals to V naught 1 minus D squared dt over 2L. Okay, so given any so if you buy a converter, boost converter, and when you buy, you find out that the L with a certain value H is Henry's, and then you have already know the switching frequency that the converter has, Fs equals to 2 kilohertz. For example, it can be 5 kilohertz, can be anything, right? So based on your converter that you bought, and then you have the diode, capacitor, and resistor, isn't it? Okay, so with that L size, you can determine the minimum size of I naught. Okay, that you can apply with your converter here before it goes into discontinuous mode operation. Okay, so and if you are in designer perspective, you are given I naught, then you can find L critical. Again, I forgot to mention during the buck converter, normally when you design your L critical, your L design will be 20% higher than the L critical. Okay, so in practical, this is what your designer or engineer does. Okay, so they try to find what is the L critical, the minimum critical, and then it will apply. Then in design, in final designs, it will be 20% larger than that L critical. Okay, to protect, to avoid the discontinuous operation of the boost or buck converter or the DCDC converter. Right, so it's straightforward there. And finally, for output ripple voltage, remember you're going to look into the capacitor current, isn't it? So for here, remember when the switch is on, you're going to have a two separate circuit, the front end, and at the output you have this circuit, isn't it? Equivalent circuit. So we know that IC equals to minus I naught, and this is simply V out over R, isn't it? So if you look at the IC, so this is your capacitor current. Okay, IC. So there will be a straight line here. Sorry. So during turn on, okay, this transistor is on, so it will be a straight line which is determined by V out divided by R, isn't it? From that equation here, and negative value. Okay, so that constant current here, capacitor current here, can be determined by this equation minus V out over R. So again, to get the ripple voltage, we always use the equation IC capacitor, isn't it? This capacitor current. So before this, we have IC equals to C dVc over dt, isn't it? And then you have that equals to delta Vc divided by dt. So you cross multiply, therefore you have delta Vc equals to integrate 1 over C IC dt, isn't it? So that gave me that equations there. Right, delta V naught equal 1 over C integrate IC dt. Okay, so again, this is only the area under the curve. So if you look at this waveform, what you get is only that area. So you want to find this area. So it is just a rectangular, isn't it? It's a rectangular area whereby the height here is equals to V out over R, and then this the base multiplied by height. So the base here, the white or height, the white is actually equals to D on, isn't it? So if you want to get the area, just simply V out over R multiplied by D on. Okay, and we know that D on equals to D multiplied by D. So that's why you have this dt now. Okay, so that will determine the ripple voltage as well as the capacitor, the value of the capacitor if you are given a spec, just like we did on the boost converter. Right? Okay. So it's straightforward. So again, practice make perfect. So you have to refer to the final exam questions again, and we're going to discuss later on, inshallah, during the tutorial on how to solve this problem. Okay, so next video will be on the buck boost converter.